Great, thanks. So I'm going to talk a little bit here briefly, a bit of a whirlwind tour about CUSP, the company that I co-founded and am CEO of, and how we're trying to take neurotechnology out of the laboratory environments, advanced neurotech, and really embed it into the fabric of everyday life and our daily applications. So I think we're all here because we recognize something very exciting right now, that we're really at a transition point in history, a cusp, if you will, of something very special, especially with respect to neurotechnology, where different areas of science and tech are starting to converge, allowing us to examine and understand new possibilities for how we interface with and really understand the brain and the mind. And some of what we're doing at CUSP is really driven by a vision that was created by Mark Weiser, who was chief scientist at Xerox PARC in the 90s, who said the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it. And to me, I used to work at Xerox PARC in the same group that Mark Weiser led. And to me, these words are incredibly fundamental about technology. Technology becomes most important when you don't recognize it as being tech, where it's just part of your life. Neurotech has not made that jump yet, but it's happening now, and part of what we're trying to do at CUSP is accelerate that transition, where the tech fades away and we can just live our lives naturally, but our brains are really being integrated into the everyday aspects of our lives around us. So let me first give a little bit of a view. I'm a neuroscientist, a computational neuroscientist, prior to founding CUSP. And so I want to give you a little bit of a view of what cognition in the lab is like. So this is this a pointer here? No. OK, so there's no pointer, but this is a typical cognitive EEG experiment. You'd sit in a lab, often in a darkened room, but not always, with kind of heavy hardware on, and you stare at a fixation cue, and you're probed, different stimuli and things like that. Try to measure the brain response to those different stimuli. Not so much different from this. If any of you guys know this very famous film, Clockwork Orange. So this is not what we think of when we think of creativity and imagination and just the human experience. It's not being fixated on a byte bar and staring at a screen. Real cognition, it's embodied. It happens out there in the world. Human life is dynamic, it's mobile. So the question that we have to ask ourselves is, how do we measure those states, those experiences out there in the real world where they're happening, get it out of the lab, and still be able to understand and measure how the brain works? Another thing that happens a lot in the lab is we have small samples, not quite n equals 1, but maybe n equals 50 or so. We take a sample, we assume 50 people represents the world. And that's not true, we all know that. There's so much variability across people, across brains, bodies, experiences. So a very key question is, how can we scale from n equals 1 to n equals everyone? What if we can have a future where we could measure everyone in the world, 7.1 billion people's neural states, measure their activity in real time, their brain activity, their body activity, the context around them? What would that allow us to learn about human cognition and the experiences? I want to show you something here. Right now, there's somebody in San Diego at the moment, and we're mapping his brain in real time on my phone. If you go to brainvis.neuroscale.io, he's wearing one of these wearable EEG headsets, and I'm seeing a 3D map of his brain on my phone in real time. I can also look at his brain networks in real time on my phone, 3G. He could be anywhere in the world. I can look at his emotion state, a neural state decoder that's measuring affect. In this case, it's just measuring valence and arousal to the best of our ability with EEG. But this is the sort of stuff we want to get to, where we can anytime, anywhere start to measure and understand people's states. What's that? What's the domain? Yeah. Oh, brainvis.neuroscale.io. There's just a Z at the end. Yeah, put it on your phones. Hopefully the 3G can support 200 people all streaming data back. It's pretty high density. But give it a shot. And emotion.neuroscale.io will give you the emotion decoder. So a little bit of a background. I did my PhD here at the Schwartz Center for Computational Neuroscience. That's in UC San Diego. With a gentleman, Scott McCaig, who's really one of the pioneers of EEG analysis, advanced computational methods for EEG analysis. These are some of the people that I worked with there in the lab at the Schwartz Center. And what we were doing was developing a lot of software for understanding neural states. The EEG Lab Environment, most widely used software for EEG in the world, created by Arnaud Delorme. Our team was really responsible for expanding that out into the many applications that have made it a real ecosystem for EEG analysis. So that includes things like LSL, the lab streaming layer, how you can synchronize different multimodal streams, brain, heart rate signals, eye tracking, motion capture all this stuff, synchronize them together, establish a common metadata format so we can start to analyze it. That was Christian Cothe's work, who's now CTO at CUSP. BCI Lab, world's largest toolbox for brain-machine interfaces in terms of number of algorithms, developed also by Christian and some of us as collaborators. SIF, the Source Information Flow Toolbox, how we can measure network dynamics in the brain in real time at the single trial level and inside the brain, not at the level of sensors, mapping it down to the cortex and looking at those neural circuits in real time at the speed of thought, really, the millisecond resolutions. That's what we're trying to get at with some of those tech. Ontologies like HEAD and S, we created open source for allowing us to categorize events, describe events in the world. Like, for instance, when you see a red ball in a game, it should be something where we can tag an event and say, this is a red ball in the context of a certain sort of task. Align that with your EEG and your biosensor data, and then you can make queries that say, give me all of the data across millions of people where they saw a red ball in a particular kind of task. What does the brain look like in that particular context? Moby Lab was technologies. This was a big thing that Scott McCaig really pioneered, mobile brain-body imaging. The idea of not just looking at the brain sitting fixated, but really in movement, when you're moving around, what is the brain and the body doing in conjunction with each other? Measuring what the brain controls, which is behavior, as well as the brain itself, in free dynamic environments. So we created toolboxes for that kind of stuff as well. So while we were at the lab, we were working a lot as well with new emerging wearable sensing hardware. I showed you one of those here, which is a 21 channel dry wearable EEG system. There's quite a few other solutions out there. At CUSP, we basically integrate with most EEG systems that are out there, as well as a number of other biosensors through this open source lab streaming layer that we co-created and maintain. And so you can see the spread where we're starting to have, not just low density systems which can measure, 1 or 2 channels of data, which are very useful, very wearable, but also very high density systems that are still free, untethered, and you can walk about in the world with. We published a paper initially in 2013, then later 2015, where we were showing for the first time that you can use these wearable high-density systems and get laboratory quality brain mapping, artifact rejection, cortical connectivity analysis, neural state prediction with these dry wearable EEG systems. So this was really, for me, an important paper because it allowed us to look at the tech that we were applying in the lab and seeing, yes, we can now start to apply this to these wearable sensors. One of the key things that we dealt with a lot there in the lab, which is a critical issue when you're trying to translate things out of that fixed lab environment into the real world, is dealing with artifacts. We developed artifact rejection technologies that can get rid of artifacts when you're moving. Here you just saw a video with me wearing a wearable dry EEG sensor jogging. While we're jogging, we can get rid of all those movement-related artifacts and get back at the brain signal, the subspace of brain activity associated with the neural states. So this was running through CUSP NeuroPipe that I'll talk about in a little bit. This is another example. This is something that we did in 2014-15, collaborating with Adam Gasly at UCSF. We created this thing called the glass brain. This is an example of it. Is there audio for this? If you turn that up, you should hear a beat. Mickey Hart, he's the drummer from the Grateful Dead. Maybe some of you guys are Deadheads here. So what we created with Mickey was an experience here. I was trying to demonstrate something that Adam Gasly's talked about a lot, closed-loop systems for enhancing cognitive performance, where you can track neural circuits inside the brain, feed that back into a game environment, and adapt the game to put selective pressure on those neural circuits. So here, Mickey Hart's in his virtual reality world, playing a game that's putting pressure on really task-switching systems in the brain. And I'm there on the right, flying through his brain in virtual reality. We're looking at the neural activity. This was using a very state-of-the-art algorithm at that time called sparse Bayesian learning. And with GPUs, we're reconstructing all these neural circuits and this neural activity with this wearable EEG. And then the idea is, could we feed these circuit activities, like anterior cingulate cortex decision-making activity, back into the game again, and and have the game put increasing pressure on that circuit to improve performance. So these are ongoing projects that we're working on with collaborators, and Adam's certainly pushing this forward as well. So again, you can see Mickey there is moving. He's free. He's unlimbered. He's doing what he would naturally do in his environment. So moving beyond that, I direct a music festival in San Diego called Mozart in the Mind. This is another example of how we've started to take a lot of this tech and really just throw it out there and allow people to create new kinds of experiences with it. So this is Mickey here again. Actually, if you click to over to the last thing, you'll kind of see an example of people really starting to move freely in this environment. Yeah, there you go. So here everyone's dancing, they're moving. It was a big 700-person drum circle, if you will, rhythm experience, and Mickey's moving, and we're getting rid of those artifacts, looking at his brain. But we did a lot of other cool stuff, too, where you could compose music with your mind, or you could have multiple people whose brains, when you're measuring the synchrony between their brains, it controls a visual or audiovisual feedback environment. So again, just a few examples of new kinds of things you can do. So in the lab, we were working on a lot of other things, too, which I think really reflect neurotechnology's transformative potential. This is not just stuff we're working on. I mean, there's hundreds of labs around the world that are really starting to push the frontier of EEG analysis and neuroscience. So some of the things that are, I think, really exciting are clinical monitoring and intervention techniques. This was some algorithms we were developing for tracking seizures using graph theory, finding those foci for seizures. Can we build better therapeutic tools using that kind of tech? Can we use EEG and network theory to come up with new biomarkers for diseases and for health? This is, for instance, looking at 148 ADHD patients' brains when they're trying to inhibit a response, something that they're typically not good at. And here we can see a circuit in the brain involving some of those areas that are responsible for control becoming hyperactivated or abnormally activated, rather. Can we do real-time neurofeedback to change those brain circuits similar to the glass brain, measure the connectivity dynamics as well? Measure affective and cognitive state in real time, brain-computer interfaces. Here's Christian Cothe wearing a system there. He's making errors on a computer task, and every time he makes an error within 200 milliseconds, we've predicted with close to, in this case, it was close to 93% accurate, whether or not he has made a mistake by picking up the neural response in the brain associated with the brain recognizing that it made a mistake in the button press. So all of these kinds of things, though, require real-world technology solutions to really take them out of the lab and put them in the real world. So the last part of my talk, I want to talk about how we're doing that at CUSP. So there's a few transformative opportunities, I think, that really motivated us to create CUSP. One is that we really need to accelerate the transition time from the technology that's evolving in the lab to the application in the real world. And currently, the time to product or the time to translation within an academic research environment is on the order of years. And that's very slow. What that means is that there's a widening gap between the progress of tech in the lab and the application in the real world. There's exponential growth in the sciences, and we want to see that same growth curve in the consumer space, in the medical space, and the spaces where it impacts people's lives. So how can we close that gap? And second, we need to have technologies that enable developers to build on existing research and development, and then very rapidly build applications that are user-facing, focus their resources on that, instead of effectively reinventing the wheel. So I advised neurotech companies for the last 10 years, and I've seen a lot of reinventing of the wheel, where a new company will come into the game, will get a new EEG headset, will have to build their own EEG headset sometimes, or maybe license some pieces, invent their own R&D, their own algorithmic stack, do years of research and development to come up with some kind of a useful algorithm, and then finally they can start thinking about building the actual user-facing part of the application. And this time scale is way too long with respect to rapid innovation. So how can we reduce that initial barrier to technology development? So this is what we've achieved at CUSP. Really the world's first platform for middleware platform for biosignal processing, neural state decoding on the cloud that allows you with a few APIs to basically access whole libraries, whole laboratories worth really of technology, and then you can just write 5 lines of code and deploy all of that tech on really any device that can connect to the internet. So Neuroscale is the name of the platform tech that allows that to happen. It's a RESTful API. So really, if your app can connect to the internet, it can be made bio-aware. I was just showing you on my phone how I was doing brain mapping. You could do that on a wearable too. You could have the lights in this room responding to the neural activity inside my brain. That's no problem at all with the Neuroscale platform. Low latency stream processing. We want to do things in real time whenever possible, although we also support batch processing. By real time, and I mean, within the time scale needed to induce neuroplasticity in the brain. So that could be anywhere from hundreds of milliseconds to even a little longer, like a second. But being able to have those kinds of closed-loop feedback applications, that's something that we're very interested in. Big EEG is something that we're also working a lot on. How do we, as we start to aggregate millions of records of EEG data, what kinds of data mining techniques can we start to apply to look at the actual, the heterogeneous nature of brain activity out in the world? I talked about that a little bit earlier. So we've developed a lot of neuroinformatics around that, much of which we've made open source, and I can talk to you more about that later. So we also built something, this was under DARPA funding, DARPA project that I was co-PI on, to build really a very easy to use visual programming interface that you could build if you want to do R&D yourself. You could quickly click together a few nodes or select from a library of hundreds of nodes, build a little processing graph within a few minutes to an afternoon that would basically represent a very state-of-the-art pipeline for doing anything from, for instance, measuring your motor intention, right, left, so you can fly a drone, or something where it would measure your emotional state, or measure your brain activity inside a specific region of the brain. So we've built this technology now. We're actually open sourcing a piece of it as a community edition, but a big stack of it is part of our enterprise edition. And the idea is if you're a lab or a company wants to do some R&D, you can click together stuff and then deploy it on the cloud with one click and access that pipeline through any internet-connected device in real time. So it really allows you to kind of scale up your R&D process. There's an example where you're clicking together a graph that builds a real-time brain activity mapping pipeline. You just drag the widgets of interest there, double-click, configure them, say these are the regions I want and these are the ones I don't. Click go, and now here it's extracting spectral activity from 4 key brain areas in the default mode network. You can then take that, as I mentioned, deploy it on the cloud with 5 lines of Python, let's say, and now you would have that accessible through this chain of 5 lines. You're now able to push data to the cloud through that pipeline and get it back on any device, allowing you to build some pretty cool stuff, like a web client, for instance, that would essentially, through your web browser, map your brain. That's what I was showing you on my phone. This is an example similar to what I just showed you, where you've got somebody thousands of miles away and you're exploring their brain in real time. Again, very little code that you'd have to write here. You just tell the system, I want this state from the person, and it would somewhat magically appear on your device. That's the goal. So some of the other things we're doing, I mentioned earlier, about ubiquity and pervasivity and being able to sort of anytime, anywhere access these states. We mean that really fundamentally. We're building a technology stack that would allow your state to be measured and monitored and integrated with the world all day long, 24/7, anywhere that you can connect to the internet. So here's an example where we're on a plane. This is probably the first demonstration of this, playing a multiplayer brain training game with people on the ground in San Diego over satellite, just on a commercial airliner. And we're controlling this game with our brain activity. As I'm modulating my attention, I lock a tractor beam on and pull it towards me. So it's a multiplayer brain training game. We hop off the plane and we jump onto the BART. And now we're on the BART. Continue to play now, switching onto 3G. Having our brains tracked, being able to have this cooperative, multiplayer brain gaming experience. These are just examples of apps you guys could build, actually. If you could click down to the first part. So this is an example now. You also in a car. So trains, planes, automobiles, you get the idea. Here in a car, this was the first demonstration of a real-time brain-computer interface for decoding, in this case, auditory signals, auditory tones, whether the person heard a target tone. We want to detect that within like 800 milliseconds on the cloud, all in real time, happening 100% on the cloud, no computation happening locally, with a dry wearable EEG system while a person's driving. So he's just driving and there's tones playing, and when one of the tones, a warning tone, pops out, it's really 15% probability you get the oddball. We can pick that out. And it was about 86% accurate, which is remarkable considering that he is moving and it's noisy and it's all dry and so on and so forth. This was using a pretty sophisticated spatiotemporal decoder, but it's no problem to deploy it in the car because, again, it happens distributed non-locally and in the cloud. This is an example now. This is United Sciences. They're building a cool in-ear EEG system using some OpenBCI hardware. And here, if you could click to the first pin on there, too, Here we're measuring steady-state visual evoked potentials from within the ear. You could do this on your cell phone with an in-ear EEG sensor, so no one would even know that your brain's being monitored. Here we're measuring the spectral activity. We can remove the ECG artifact in real time from the in-ear sensor. If you click to the second one, this is showing in NeuroPipe how you can just really easily configure pipelines and dynamically wire them up to view different states and different features of the neural data. And then again, all this deploys on the cloud. Piloting drones with your mind. These are some students. We want to make things really easy for you to use. So this is an example where these are bioengineering students, never used EEG before in their life. I mentor a number of bioengineering seniors at UCSD, and here their goal was to build a hybrid quadcopter control system where they could fly a drone with their eyes and with their brain, so they could get 5 degrees of freedom control. That was the goal. And so here they're using a motor control. When he's imagining left, imagining right, he can steer the drone. This is using NeuroPipe. Games, I mentioned that earlier, cognitive neurogaming, very exciting area for development where you can have adaptive games that really change the brain, promote enhanced brain health. This is another example of a kind of an app that you could build. These are collaborators at Brain Rhythm Incorporated, company in Taiwan, and Army Research Labs. They built a game that allows you to sort of, when your performance is declining in the game, it kicks in a little in-game, and you do a neurofeedback game to basically modify your brain state. So this is another one where you can, in VR, fly game up, down. He's basically piloting it with piloting a spaceship just with simple state like attention. Just some more examples of things you can do. This is actually in VR, multiple person, new creative experiences with other people, where in this case, as brains start to synchronize in terms of people entering into the same neural state, you start to adapt an artificial life world in a creative way. So the idea is really to create a system for this game where in VR, you and other people sort of get into the same neural state, and you get feedback through that, reward feedback by the fact that new artificial life forms are created, which is really the objective of the game. Anyway, this is just a fun experience that was created by Sheldon Brown and some others at Cal IT too, powered by the Neuroscale Platform.
But it's working.
And I just want to leave one little example here where so you could actually mute that real quick. So plug and play Neurotech for everybody. I mean, I mentioned how the students were able to build their thing. This was just a few days ago in Budapest. I just got back last night from Budapest, where we were running the world's largest hackathon along with several other collaborators for brain and vision. We had 180 people there. This is a group of Slovenian students, never had seen EEG before. Over the course of the night, they were able to build a functioning BCI on Neuroscale that allowed them to power properties of the game based on 3 different neural states. They built their own pipeline, deployed it, got the whole thing up and running, and they won one of the prizes on account of that. So the idea is make it easy to use and make it something you can access anywhere. And then just kind of, thinking a little bit beyond EEG, what's the next step? Implants, invasive technology. These are some of the things that we should be thinking towards, and the kinds of technology we're building are really trying to power that as well. So here's an example. This is at University of Ottawa. They're doing clinical trials around the BrainGate system. And here there's a person who's learning, basically it's kind of matrix-like. The person's has an implant in their brain. There's various decoder models that are running. Some now they're running on NeuroPipe. And what that's doing is controlling a virtual prosthetic in a VR environment. So the idea is instead of learning to have to control the robotic arm in physical world space, instead you control it in virtual world space, and you can enhance that neuroplasticity, and then you can eventually translate it to something in the real world. But this is kind of a precursor to what I think is going to happen as we're starting to move towards matrix-like stuff. If we want to move there, and that's a big question that we all have to address ethically. Just my very last example, I showed you the emotion state decoder. Yeah, it really is a big question, and we should have an ethics discussion afterwards about that. But anyway, there's a lot of lives that can be helped in the meanwhile as we move towards that tech. But this is an effective state decoding method. I just showed you that on my phone earlier. One of the cool things about this is that, one, it works kind of out of the box in the sense that it's about 76% accurate, even if it's never seen any data from you. And it does better if it sees data. But you can get this on your little cell phone. You can track over the course of the day. Imagine one of you guys could build an app that tracks over the course of your day, syncs it up with your calendar and all the other things that are happening in your life. It tracks your affective state and gives you personalized feedback on what you should do to sort of optimize your affective state over the course of your day. So I want to leave you with this one slide. because I think I've run it a little bit over time, which is just that you can have in the future experiences, or really, I don't even call them experiences, having your brain integrated into the world around you in a very seamless way, where, for instance, you could have your house, your lights, your thermometer, your temperature, the various things you interact with that are all adapting in a control feedback way to move you towards the desired state. And this is not a fantasy thing. I mean, there's a lot of work in control theory over the last 80 years that show that control systems, the mathematics behind it, could be directly applied to this sort of problem. And so it would be really cool to think about that. Like, what if we had that kind of experience where the world around us was shaping itself subtly to sort of move us and promote into positive directions and promote a desired neural state? I think this is the next generation of where neurotech is also going. So I'll leave it there. I've rambled on for long enough. But if you're interested in signing up for the beta, go to cusp.io and sign up. If you're interested in learning more about wearable neurotechnology and the research behind it, feel free to talk to me later. Thank you for your time.